Alright, hello class. In this video we're going to be talking about Talyor series. And really you could probably, without much instruction from me, kind of get the gist of how this works. A Talyor series is basically we take the Talyor polynomials and just take the limit as n goes to infinity, and it leads us to this Talyor series. Alright, and it basically works exactly the same way. We find the terms the same way. We can analyze the interval of convergence, radius of convergence in the same way. They're just very specific series. Okay? And the importance with them, though, is if you remember, we got better and better approximations using polynomials when we took the degree higher and higher. So, in other words, if Pn of x was the Talyor polynomial approximation of some f of x, right? Well, we know that the polynomial is going to be really close to f, 4x is close to a, but this approximation gets better and better. So it gets better and better as n gets larger. Okay, so what that means is if we take the limit as n goes to infinity of Pn, right, which gives us a series, so this is now the Talyor series versus just the Talyor polynomial, we will actually get equality. Okay, and we'll get equality wherever the series converges. All right, so we check that the same way we did back in the previous video. We find the Talyor series by the same process we did in that first section where we're finding Talyor polynomials, but once we find that pattern, we can create a series out of it. Okay, so really we've done most of the heavy lifting. Now what I want to show mainly is I want to give you some of the well-known Talyor series, and I want to show you what you can do if you need to find a new Talyor series without having to do all of that work that we've done previously. Alright, so our first famous Talyor series is e to the x, right? And we get that one, basically, it's 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, on and on and on. So really, it's the series k going from 0 to infinity of 1 over k factorial times x to the k. All right, so as I mentioned in one of the earlier videos, this is kind of the ideal Talyor series because it's really just the one where all of those derivative of f things end up being 1. All right, then I'm going to give myself a little more room here, actually. Okay, so I shifted some things over, moved this over here, and cosine of x was all of the odd terms of this, but alternating. So it was 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, etc. So how we write that in the series notation. Okay, so we need an alternating piece. So that would be negative 1 to the k. All right, and we can start at k because when we plug in the 0, we'll get 1. All right, then it's going to be x to the 2k all over 2k factorial. This is how we make the even terms. I think I showed that in a previous lecture. How you do even is with 2k. How you do odd is 2k plus 1 or 2k minus 1, depending on which one you are trying to do. But when you put in k equals 0, you get 0 factorial raised to the 0, so you just get the negative 1 to the 0, which is 1. When you plug in the 1, you get 2 factorial here and 2 here. And when you plug in the 1 here, you get a negative 1, right? So that works out. Sine is the odd terms alternating. So it would be x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7, and on and on. So how we do that one? All right, well, we get the same alternating guy. We can put that in, and it will work the same way, because when we put in the 0, we'll start with a positive. When we put in the 1, we'll get the negative. Okay, and then here, I'm going to want to do, I think, 2k plus 1 in the exponent and in the factorial. And because of that, that's because when I plug in 0, I'll get 0 plus 1, so I'll get x to the 1 and then 1 factorial, so that will be that. When I plug in 1, I'll get 2 times 1 plus 1, that will give me 3 and 3, so that's exactly what I want there. Okay, now another one you might not think about actually comes, and we talked about it a little bit before, but it's this function here, 1 over 1 minus x. Okay, this is going to be 1 plus x squared plus x cubed plus x to the 4th, on and on and on. Okay, so that's going to be k going from 0 to infinity of x to the k. And I know that that's what this ends up being because this is a geometric series. Now this guy only converges, so this only converges on essentially negative 1 to 1. That's where the absolute value of x is strictly less than 1. Okay, so those are some famous Taylor series we've already sort of found. We found another one recently. Let me put that one up. We'll just continue the path. All right, so it was, we had found the Taylor polynomial for 1 over x, and it was, we had to center it around 1 because we couldn't plug zeros in. So if you remember, it looked like this. It was 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed plus x minus 1 to the 4th. So actually in the next piece is a minus. So it looks like to me what we have is we have an alternating piece, so that's always -1 to some power. So I'm going to start at k, because when I plug in the 0, that will give me a positive. And then it will be x minus 1 to the k. Alright, so essentially, with these Taylor polynomials we've already found, if we have a pattern that we can continue, we can, well, continue it and just create a series out of it. The only thing we have to worry about, if you remember when we did like the square root of x plus 1, a nice pattern wasn't actually making itself clear to us. So in those cases, that might be a little trickier. But, you know, for the most part, the work we've already done in this first section of the module is going to carry over. All right, now here, the radius for this one, for e to the x, our radius of convergence is infinity. Our interval of convergence is -∞ to infinity, and that's true for all three of these. Okay, these will converge everywhere. Very nice. I've already talked about this one because we already know that this is a geometric series. This one, it may not look like it, but this is actually also a geometric series. So if I were to sort of adjust this, say these are both raised to the k, so this would be the series x, or k goes from 0 to infinity of, when I bring that -1 on the inside, this will be 1 minus x raised to the k. So this will converge for the absolute value of 1 minus x strictly less than 1. So if we sort of mess with that a little bit, all right, and then subtract 1 on both sides, so I'll get -2 is less than -x, which is less than 0. And then when I negate everything, we have to change the signs to do that. So it'd be 2 greater than x greater than 0. So the interval of convergence here is 0 to 2. However, the radius of convergence is still just 1, because it's half the length of this. Okay? All right. So it has the same radius of convergence as this geometric series, it's just shifted over. Okay, which actually makes some sense because this is literally just shifting this one over and then alternating it. Okay. All right, so let's find the Taylor series for f of x equals the natural log of x plus 1. I'm going to use, of course, a equals 0. I'm always going to want to center these around 0 whenever I can. I will say that a Taylor series centered at 0 is called a Maclaurin series. I think it's like this. I don't often use this terminology. I just say a Taylor series, and I just take for granted that it will probably be centered at 0 unless it can't be. But a Taylor series can be anything. A Maclaurin series is always centered at 0. I don't know why the book bothers with that, to be honest. They're all Taylor series, right? A Maclaurin series is a Taylor series. It's just a very specific one. Anyway, so sometimes the book will ask you to find the Maclaurin series for a function, which really just means find the Taylor series centered at 0. All right, so to do this, remember we're going to need to find a lot of derivatives. So let me write the function again here. It's a natural log of x plus 1. Then f prime, we're going to be using the chain rule a lot, but thankfully the derivative of the inside is 1. So the chain rule should not really make much difference here. This will just be 1 over x plus 1. And now this is, let me write it like this. This is 1 x plus 1 to the negative 1. And now when I start taking derivatives, the second derivative will be negative x plus 1 to the negative 2. And here's where it's nice to not need to worry about the chain rule because the derivative of the inside is 1. Okay, so now we'll get 2 times x plus 1 to the negative 3. Then we'll get the fourth derivative is going to be negative 3 times 2 times x plus 1 to the negative 4. Now, a question I get a lot is, how far out do you need to go? And usually I go to about 5 or 6. I just want to get to a pattern. Okay, so, and I'm starting to see it now. Because when I take the sixth derivative, I will have now, it will be negative 5 times 3 times 2 times x plus 1 to the negative 6. So we're getting essentially factorials here. Okay, now when I do this, I start to simplify the terms themselves. So remember, if we're centering this at 0, f of 0 is going to be, thankfully here, 0, because when we plug 0 in, it's natural log of 1, which is 0. Okay, f prime of 1, of 0. Well, we're just going to plug 0 into here and we get 1. Okay, f double prime of 0 over 2. Okay, well, again, this piece just becomes 1, so we get negative 1/2. F triple prime of 0 divided by 3 factorial. Well, this is going to be, from here, 2 over 3 factorial, which is, and here's why I write it like this, because now this is 2 over 3 times 2. All right, and those 2's cancel nicely, and we get down to 1/3. All right, then the fourth derivative, I'm not exactly balanced here, but hopefully that's okay. At 0 over 4 factorial, well, we're going to get, this is negative 3 factorial, or I'll just put negative 3 times 2, and then down here, this is 4 times 3 times 2. So these guys cancel, and now we're left with negative 1/4. The fifth derivative at 0 over 5 factorial. Well, this right here, 4 times 3 times 2, that is 4 factorial. So this is 4 factorial all over 5 factorial, which is 5 times 4 factorial. Oh, the factorial cancels, and we get 1/5. All right, then the sixth derivative over 6 factorial. Well, check this out. I left off a piece, didn't I? Sure did. Sorry about that. This should be negative 5 times 4 times 3 times 2. So this is negative 5 factorial over 6 factorial, which is 6 times 5 factorial. And hopefully you see the pattern by now. This is negative 1/6. So the Talyor series, right, for this function, f of x, which is the natural log of x plus 1, ends up being, okay, it'll be 1 minus 1/2. So here's what we have to be careful with. Actually, let me write this. The first term was actually, 0. Okay, so we can't forget that. The first term was 0. there'll be plus 1 times x minus 1/2 times x squared plus 1/3 times x cubed minus 1/4 times x to the 4th plus 1/5 times x to the 5th minus 1/6 times x to the 6th, and it will likely continue in that pattern. So this is going to be the series k going from 1 to infinity of -1. I should probably do k plus 1 because I want that first term to be positive. Okay, so it'd be -1 times x to the k over k, right? Because at each k, so here's k equals 0. Well, we don't even need to bother with that because it's 0, and we don't really want to put that in this because we'd be dividing by 0. Okay, then this is k equals 1. This is k equals 2. This is k equals 3, 4, 5, 6, and how it always works, we have an alternating piece, and then we have it's always x. So here it's x to the 1 over 1. Here it's x to the 2 over 2, x to the 3 over 3, x to the 4 over 4, x to the 5 over 5, etc. Okay. All right, so there's the series for the natural log of x plus 1. The next question is, where does this thing converge? Okay, so where does this converge? All right, well, we'll use the tricks we talked about last time using the, I'm thinking ratio test here. Yeah. Since the whole thing isn't raised to the k, for a ratio test, or r, will be the limit as k goes to infinity. Okay, the absolute value of the k plus 1 term. What I'll tell you is we don't even need to worry about this since we're taking the absolute value. So we can just go straight to x to the k plus 1 all over k plus 1 times the reciprocal, which will be the absolute value of k over x to the k. And k's are not that easy to write on this tablet. Neither are straight lines, apparently. So this will be the limit as k goes to infinity of, when I simplify this down, it will be the absolute value of x raised to the k times the absolute value of x all over the absolute value of k plus 1. And actually, we can drop the absolute value here because k will always be positive, then times k all over the absolute value of x raised to the k. Right? And here the absolute values of x raised to the k's, those guys cancel, and then we're left with k over k plus 1 and an absolute value of x. And just like before, we can take the limit as k goes to infinity, and actually we can move that absolute value of x outside and just focus on the limit here. And the limit here, it goes to 1. Okay, so this comes out to just be the absolute value of x. So r is equal to the absolute value of x, and that means this series converges for the absolute value of x strictly less than 1. Okay, so that means the radius of convergence, capital R, is 1, and the interval of convergence, we've seen this one a number of times now, it's -1 and 1. Okay, and I'm going to leave this as I star because I'll leave it to you to check the endpoints. Okay, just see what you get on the endpoints there. What's important here is really the radius of convergence. All right. Now, what you'll probably be able to tell just by looking at it, this guy should not converge for -1, because if we put -1 in here, we get natural log of 0, which is garbage. If we do put in 1, we should get something kind of familiar. Okay, so as you've probably recognized, either from the previous sections and what we've just done here, this is quite a bit of work just to get one series. So what we want to be able to do is piggyback off of this, and it turns out that there's a lot of stuff going on behind the scenes. I don't want to bore you with all the details, but it turns out that if a series converges, and I should say if a Talyor series converges, then products and substitutions, so then products, compositions, derivatives, and integrals of the series will also converge. Right, so this is actually kind of huge because we can say if I have this series, the natural log of x plus 1, and I want to find the Talyor series for, let's say, the natural log of 3x plus 1, well, all I need to do is actually just plug the 3x into the series that we have, and it will also converge. So it's really just this. I've replaced x here with 3x here. So that means every x here will get replaced with 3x over here. So it will literally just be the series k equals 1 to infinity, -1 to the k plus 1 times 3x raised to the k all over k. Okay, now this one, we know this one converges for the absolute value of x less than 1. That's what we established before. Well, now this one will converge for, instead of just absolute value of x less than 1, we're going to replace the x with the 3x. So it'll be 3x less than 1. So this tells me that we can break this down as 3 times the absolute value of x. So it's going to converge for the absolute value of x less than 1/3. Okay, so there's a lot less work to do here. If we already know the series for the natural log of x plus 1, we can just plug in a new value. Now, it will change, sometimes it will change the radius of convergence. So the radius of convergence here is 1/3. It's smaller than this one, but we've made the inside here that we're raising larger. Therefore, it will shrink the interval that this series converges on. Now, here's a really important bit. I can, if I have that, okay, the natural log of 1 plus x, or x plus 1, is this series. Right, as long as it converges, and where it converges, we can actually, and let me write some of these terms out. That was, right, 1 minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc. We can actually differentiate this, and it turns out we can do it term by term. And I totally wrote this wrong, didn't I? Sorry about that. It's 1 minus x. Sorry, no. It's, 1 times x. So it's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So mostly right, just I had an extra term in there. Sorry about that. All right. So we can, the important part is we can differentiate this term by term. So the derivative of the natural log of 1 plus x is 1 over 1 plus x, which I can actually bring the derivative inside the Talyor series, provided it converges, and where it converges, this will work. If it doesn't converge, then, you can't do this. And it won't, work where it doesn't converge. But we can just differentiate this term by term. So let me actually get a few more terms here. Let's go out to 6. Okay, so the derivative of x is 1. Derivative of x squared over 2 will be negative x plus, well, the 3 comes down and cancels with the 3, so it'll be plus x squared, be minus x cubed plus x to the 4th minus x to the 5th, etc. In fact, if we were to differentiate this in terms of the k's, the constant would remain unchanged. We'd get negative 1 to the k plus 1, so that part doesn't change. We'd get k times x to the k minus 1 all over k. The k's would cancel, and now we just get k going from 1 to infinity of negative 1 to the k plus 1 times x to the k minus 1. All right, and this may seem like a strange, this doesn't maybe look like this does, but we might need to alter the way it's ordered. All right, so we could do k going from 0 to infinity, and actually let me use a different letter here. Let's call this j. Right, and so I need an alternator. So it starts at a positive value, so that means I could start the negative 1 at 0. That would make it positive. Then times x to the j. Okay, so that means at j equals 0, we get 1. At j equals 1, we get negative x to the 1. J equals 2, we get plus x squared. J equals 3, we get negative x to the 3rd. Perfect. So this is, I'm back to j here, j going from 0 to infinity of, this will actually be negative x to the j, which is a geometric series and will converge to this 1 over 1 minus a negative x for the absolute value of negative x less than 1. Oh, well, check this out. When we simplify that, we get all the way back to this. Okay, so it turns out that we can actually differentiate term by term, okay, and get the series for, say, the derivative of the natural log of 1 plus x. All right, and notice the radius of convergence is the same. Okay, so what's happening on the endpoints might not be, right? The endpoints could change when you do this, but the radius of convergence will stay the same. Okay, so this is something we can do to really help us find a series way faster if it's based on a series we already know. All right, so this also works with integration as well. So I want to find the Taylor series of tan inverse of x. However, I do not want to go through that process that we've done. So I'm going to try and use a series that we've looked at before. So the derivative, if I look at the derivative of tan inverse, remember that comes out to be 1 over 1 plus x squared. Okay, now 1 over 1 plus x squared, that does seem similar to a series we've already looked at. Right, so this would be similar to maybe the 1 over 1 minus x, the geometric series. Now, we could also do the 1 plus x, but how we make this is I want to plug something into this so that it looks like this. Okay, so if I were to do 1 over 1 minus a negative x squared and plug that into this series, I'd get the series from k going from 0 to infinity of, sorry, I did that totally wrong. That's a negative x squared. I need to not square the whole thing. Sorry about that. So this will be negative x squared raised to the k. Okay, so this is going to be the series k going from 0 to infinity of, I could split this up as a negative 1 to the k times x to the 2k. Okay, so to me that looks like an alternating geometric series with just even powers. So when we plug in 0, we'll get 1. Then it will be minus. So when we plug in 1, we'll get 2 here. So it'll be minus x squared, and plus x to the 4th, minus x to the 6th, plus x to the 8th, minus x to the 9th, plus x to the, not 9th, 10th, plus x to the 12th, minus x to the 14th, etc. Okay? So this actually does simplify out to be 1 over 1 plus x squared. So it doesn't take that much work to show that the series for 1 over 1 plus x squared is this. And thankfully, we don't have to go through all that work again. All right, so this is 1 over 1 plus x squared. Now, importantly, I can integrate to get tan inverse, right? Tan inverse of x is what you get when you integrate 1 over 1 plus x squared dx. So we should similarly, just like with derivatives, we can do the same thing with integrals and integrate this piece by piece. So this would be 1 minus x squared plus x to the 4th minus x to the 6th plus on and on and on. And we try and throw a dx at the end. Now we're not going to mess with a plus c, okay? When you're doing the series stuff, don't mess with a plus c. It's not necessary. Okay, So the series for tan inverse of x, I'll just start integrating this and see if I can get a pattern. All right, so the integral of 1 is x. The integral of x squared is x cubed over 3. Integral of x to the 4th is x to the 5th over 5. Minus the integral of x to the 6th is x to the 7th over 7. Plus, that will be x to the 9th over 9. Minus, we had the x to the 10th here, so I'll do one more step, x to the 11th over 11. Okay, and if I had this written out like a series, we could integrate this term by term. So the constant's not going to change. That negative 1 to the k won't change. All we do here is we add 1 to the exponent and divide by it. Okay, so this is the series representation of tan inverse. All right, so when we, if we try and verify this, when I put in the 0, this will become a positive 1. We'll get x to the 1 over 1, so that's x. When k is equal to 1, I'll get negative 1 to the 1, so it's a negative. This will become a 3 over 3. And when we put in k equals, so that was 1. When we put in k equals 2, we'll get 4 plus 1, which is 5 over 5 here. And this will be negative 1 squared. So this is aligning with what we saw there. So here's an interesting result from this. Okay. From this series, I want to show you something. If I take tan inverse of 1 and plug it in my series representation for it, all right, this will be negative 1 to the k times 1 to the 2k plus 1 all over 2k plus 1. So what this ends up being is literally just the series k equals 0 to infinity of negative 1 to the k over 2k plus 1. Okay? Now, tan inverse of 1, well, the angle that makes tan inverse 1 is pi over 4. Okay? So pi over 4, well, based on this, tells me that if I plug 1 into, if I plug 1 into this series here, I'm going to get 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th, etc. Turns out that this particular series, the alternating series, 1 over the odd numbers, actually equals pi over 4. And it's the Talyor series that actually finally get us to the answer of, well, okay, we can check to see whether a series converges, but what does it converge to? The Talyor series can help us with that because, for example, this series here, k equals 0 to infinity of, let's say, 3 to the k over k factorial. That's likely a series we looked at in the previous module. Well, this is actually going to be equal to e cubed because e to the x is the series k going from 0 to infinity of x to the k over k factorial, and when you plug in 3, you get this series k going from 0 to infinity of 3 to the k all over k factorial. So this series here actually, previously we could prove that it converged, but now we have the knowledge to tell what it converges to. it converges to e cubed. Okay, but to get to there, we needed some calculus, we needed some other things. A lot of these things we haven't quite proven yet, but that finally is what answers our question. Okay, we can test to see that it converges. What does it converge to? Well, if it's the Taylor series for a known function, then it converges to that value. All right, so I think that's probably enough brain melting to throw at you in one day. And that should totally get you rolling on the homework. So I will catch you all on the next one. Cheers.